Okay, I'll introduce myself again. I'm Sarah Vaya. I'm a professor and climate extension specialist at the University of Maryland. And today we're talking about progress in the energy transition. This has been really interesting for me to prepare. Some of you know I spend a lot of time preparing these things and reading as much as I can. And there's just a fire hose of information about this, which is really exciting. And I hope to cover all of the essentials and a lot of the interesting material today. So, which future do we want? The speed of the energy transition, which is one of the big climate solutions, is absolutely up to us. So hopefully you'll learn a little bit today to make some choices about that. Okay, so definition time. The energy transition is the whole process of switching out from fossil fuels to wind, solar, and geothermal for generating electricity, doing our heating, and conducting various transportation, cars and trucks, et cetera. Now, why do we need this change in the first place? Again, I know most of you know this already, but you will realize that carbon dioxide, CO2, and methane from burning fossil fuels and also from obtaining natural gas that causes a lot of methane to be leaked to the atmosphere. These two things are the biggest cause of climate change. And you can see in this graphic here, this is annual emissions. The emissions in the world are, really rapidly increasing, again, mostly around from 1950 on. And you can see this and the corresponding increase in temperature. There's a little blip here in 1940. This is pre-industrial. Little blip in 1940 due to something else not having to do with emissions. But a clear trajectory upward that you can see after about 1960 that corresponds to this increase in emissions of carbon dioxide and methane. Here's the temperature increase in 2024. I know all of you are probably aware that this has been the hottest year ever, the hottest January, the hottest February, et cetera. And this is what Berkeley Earth thinks is the probable range for 2024, but I suspect this is what we've had up to date. I think it'll probably be closer to this. So we're really accelerating this process. And once we stop emitting a bunch of fossil fuels, it won't cool off right away. It'll take some time for that to happen, but at least it won't be accelerating like this. Okay. Burning fossil fuels to make electricity or power cars or other vehicles is not just polluting. It doesn't just cause climate change, but it's very, very inefficient. This may surprise you. When we use coal, for example, to generate electricity, here's a coal-fired power plant, most of it is lost as heat. Only about a third actually goes to the plug as electricity. So this is a giant waste. We mine the coal, we transport it, we deal with all the environmental impacts, yet 2/3 of it is wasted. Solar as a primary energy source is 250%, that's 2.5 times more efficient than coal. Let's talk about our vehicles. When we put gas in our car, up to 88%, almost 90% of that in some cases is lost as heat, in very inefficient cars. Only 12 to 30% moves the car down the highway. Again, very wasteful. An electric vehicle is 400% more efficient than an internal combustion engine, ICE, or 4 times as efficient as a gas or diesel powered vehicle. And so, we're just wasting a ton of energy. So this means that less overall energy will be needed after we transition off of fossil fuels. Without all this wasted heat, we'll need only about 60% as much energy as we now obtain from fossil fuels. Plus, there won't be any ongoing mining or drilling, okay? We won't need to be continually coming up with fuel for the process. Okay. Now, once the infrastructure for clean energy is built, renewable power is nearly free, right? Wind and solar the fuel itself doesn't cost anything. So this is really, to me, really important and really great because once we have a renewable power economy, oil and gas can't be used for political gain or to push countries around. And oligarchs of these countries are not going to be making a ton of money off of us. No new fuel is needed, as I've already talked about, no ongoing drilling or mining or any of that stuff. And wind and solar energy will provide abundant power to the 45% of Earth's people who now have little or no access to power. So a lot of people in Africa, a few people in South America, Central America, and in Asia. I'm sorry. This graph shows us where wind and solar potential is super abundant. Sorry. Back to the point of no access. A lot of people in Africa and other places don't have access to power. They don't have lights. They can't read at night, etc. So this map shows where wind and solar potential is super abundant. Okay, here we are. And then really abundant, 100 times what we demand, or the energy demand. And then replete, that means 10 times. And so we're in the 10 times category. But wind and solar providing 10 times what we need is, hey, pretty abundant in my book. So this will, the transfer to wind and solar away from fossil fuels will really be an equity revolution, a revolution in environmental justice, as well as reducing the rate of climate change. Okay, clean renewables, wind, solar, geothermal, also save a lot of money by benefiting not only climate, but also health. So this picture over here shows us that wind and solar will avoid a lot of emissions of carbon dioxide. Well, we already know that. It will avoid a lot of nitrogen oxide being emitted into the atmosphere. Nitrogen oxides like nitrous oxide, that's a potent greenhouse gas, or nitrogen dioxide, which is really harmful gas to breathe, and it can cause a lot of health impacts. Sulfur dioxide, also not that great to breathe. These are avoided by switching over to wind and solar. This will save a lot of money. Reduced emissions from reduced climate and air quality damage will, this is a sort of weird sentence here, but the point is it's going to save us $249 billion in the, or it already did save us, between 2019 and 2022. That's a lot of money, okay? And you don't notice that this is happening, but it's still saving a lot of money. There are also documented health and climate benefits just from wind power. And this is a kind of cool map. It shows for different regions of the country how much is saved on health and climate damages per megawatt hour, MWH, megawatt hour. So in the Mid-Atlantic where we live, switching over to wind power saves $140 per megawatt hour in health and climate damages. So nationally, on the average, wind saves $162 per megawatt hour. And that's much more than the average cost of wind power, which is only $52 per megawatt hour. So we save as 3 times as much in damages as we spend for the wind power. So in my book, that's a pretty good bonus. And finally, this just came out 2 days ago in The Guardian. The increase in clean power under the Inflation Reduction Act, and I'll talk more about that in a minute, is predicted to save 200,000 lives over 10 years. So that's also a really big bonus. Okay, there's 3 key components of the energy transition. Deploying clean energy on the grid, okay, grid scale deployment. That means building the wind turbines, building the solar arrays, et cetera. Enhancing grid infrastructure and expanding the grid, building new transmission lines, doing things to make transmission more efficient, And finally, boosting energy efficiency, which means that we don't need as much power, so that's all good. And demand side flexibility means this will feed into what I'll talk about near the end of the talk about virtual power plants, where utilities can basically ask residents or buildings to reduce the demand by turning down their air conditioning or whatnot, and that produces a lot of flexibility. So I'll talk about that more at the end. Now, how long do we think this is going to take? Now, I'll just give you the big warning right here. Like pretty much everything we want, it's going to take longer than we hope, but less time than we fear. And this is so just keep that out there. It can be frustrating at times to wait for things to happen like this. Okay, the great thing though is that the transfer, the shift over from fossil fuels to clean sources of energy is not going to plod along on a straight line. This is time, and this is, say, market share for wind or solar. And the whole issue here is how fast does it take to increase market share for one of these clean things. So this does not proceed along this green line, which is basically at a constant rate, but instead it proceeds on this curved line, which means that you can when you start out, everything's really slow. And we're all thinking, we're never going to get anywhere. It's going to take forever. And it would if we were on this line, but because we're not on that line where this process is following this curve, the S curve, and you can see it looks sort of like an S. That's why it's not a linear process. And so about the time that things start to speed up, this is called the tipping point. And if we just look at this point, which is about 5% of market share or 5% of new sales, it varies. If in fact we were following this line, by the time we got to 50%, by the time we got up to this time period, we'd only be at 13%, okay, if we were on the line. But at the same time, if we're following the curve, we're at 50%, okay? So I'm sorry, I didn't explain it very clearly. But the cool thing about this S curve is it takes the same amount of time to go from 0.2%, okay, a really small amount of, say, wind or solar, to 5% as it takes to go from 5% to 50%. So you can see that things really speed up, and that is going to help us out a lot. So the energy transition, that is the change from fossil fuels to renewable, is going to be on the S curve. The sale of EVs on the S curve, the deployment of solar panels on the S curve. And the other great thing here is that once we get past this tipping point, change is not only rapid, but it's pretty much inevitable. Okay, so it's not gonna stop. Okay. Now, past technology shifts have pretty much followed the S curve, and I've learned a lot from the Rocky Mountain Institute reports, and this is from one of those. So going from gas to electric lights, or from steam to electric power, or from coal to gas heat, you can see this is electricity. It's basically increasing very rapidly. You don't see when it tops out. Here's a steam to electricity. Here's coal to gas, excuse me, gas is taking over from coal, electricity is taking over from steam, very, very rapidly. And from what we can tell from the early days on wind and solar generation and EV sales and battery storage battery sales, renewable energy is going to follow that very same path. So we're going to be going up the S curve, and it's going to get more and more rapid until we pretty much saturate the market, and then we'll be in great shape. Okay, so what drives the S curve? Why do these sort of transitions follow this S curve? Well, for most of these transitions, the cost of the new technology drops as people get experience with it. There's more manufacturing, et cetera. So with more experience, more use, and then of course there's the economy of scale. you're building 100,000 windmills a year, I just pulled that figure out of my hat. I don't know how many they build a year, but if you're building a lot, then it doesn't cost as much to build each one, right? So there's an economy of scale. So the people in this business have coined this term called the learning rate. As a college professor, this is not what I think of as the learning rate, but it's defined as the price drop with each doubling of deployment. Okay, so here's a picture of what the learning rate for solar looks like, starting back in 1976 when this is, I think it's the price per watt. The price of solar, I think it's price per watt. I'm not exactly sure about that. But the price on some scale has declined basically very, very, very rapidly as we have gone through time, okay? And so the learning rate for solar, the price drop with each doubling has been about 20%. Every time you have twice as much solar, the price has dropped by 20%. Learning rate for wind, a little bit less, 15%. But this is great because it turns out that when you have this kind of rapid drop in price, the whole system enters this sort of positive feedback loop. And the idea here is that technologies that become cheaper with increasing production enter what they call a virtuous cycle, which I think is great, virtuous cycle. More deployment, prices fall, okay? So prices fall because of the learning rate and also because of incentives. So prices fall, the thing becomes more competitive in the markets it's already in and competitive in new markets. So demand increases, more solar panels or more wind turbines get purchased, more deployment, prices fall, more competitive, demand increases. So this is a positive feedback loop, if you will, boosted by the learning rate, okay, how much cheaper they become, and various incentives. So let's talk about federal incentives in the US. Most of this webinar is going to focus on the US, although I'll say a few things about global patterns. So there have been two huge bills passed in the last few years, the Inflation Reduction Act passed in August of 2022, and the Bipartisan Infrastructure Bill passed in November of 2021. IRA, Inflation Reduction Act bill, Bipartisan Infrastructure Bill. So these pieces of legislation have provided a lot of funding for important changes in the sort of energy transition. So residential energy efficiency improvements, $14 billion going to that. Efficiency and energy, okay, so a lot going to that. Wind, solar, and storage tax credits, 128 billion. Manufacturing credits, 37 billion. Nuclear credits, 30 billion. Now, here are a few which I sort of call out as what I think of as giveaways to special interests. Tax credit, 3.2 billion for carbon capture and utilization. Okay. I gave a webinar last year on fake climate solutions. Okay, I think this is one of them. Clean hydrogen tax credits. I don't think clean hydrogen is going to be as important as they say. And none of the hydrogen made now is clean. It's all made with methane. So there's a very painful transition there to start making hydrogen with clean energy, clean vehicles, clean refueling, biofuels incentive. I think some of you also know that biofuels like ethanol for adding to gas is in fact not a climate solution. Making the ethanol for the gas actually causes more emissions than just burning the gas. And I've talked about that in a webinar as well. So some of these same things are also incentivized in the bipartisan infrastructure bill. So this is going to boost production of clean energy, create a bunch of jobs up to 1.3 billion, reduce costs, okay, as I said in the last slide. The residential rebates are going to increase the installation of residential solar and increase energy efficiency, et cetera. And these things will change social norms. It turns out that one of the biggest predictors of whether or not a neighborhood will install solar panels is whether one family has already installed the panels. if once that happens, people see the solar panels on the roof and they're like, well, I think these folks are reasonable and intelligent. And if they think it's a good idea, then maybe I'll put solar panels too, and they talk to you or whatever. So this is how social norms get changed. All of these things speed that virtuous cycle. Okay, but at the same time, things don't always go so smoothly. And it's really important to expect setbacks. Over the past 2 years or 2 years, we make some progress and then something will happen. And I'll be like, oh no, and it's like up and down, up and down. But this is something we just have to expect. So here's a great picture from the Rocky Mountain Institute, which basically shows how these transitions proceed. Here's the sort of old technology going along, and there's a peak and a plateau. But during this plateau, before we really start to see a good decline, there's going to be a bunch of disruption and bumps, essentially. But here's that S curve. Okay, we're around here somewhere. And as the new technology starts to speed up, this old technology drops off the cliff. Okay. So some events speed this transition up. So like the incentives, for example, that I just talked about, ongoing price drops and efficiency increases that speeds things up, clever solutions to problems that come up. I know we've all heard about a lot of the problems with wind and solar and whatever, and transmission. There are a lot of really smart solutions out there, and this makes me feel very optimistic. Other things, as we were going along with the good news, other things slow down the transition. So rising energy use, with more people buying electric vehicles and all the increase in heat, et cetera, we're getting and we're having about as much as a 9% increase in energy demand per year in the US. There are some delays coming, in making the rules for these IRA incentives, which has sort of held the money back a little bit. And then there's always the incumbents, that is the people who are in charge of the old technology, the fossil fuel corporations and the people who are paid by them, which is pretty much everybody in the government. The incumbents fight back with a lot of disinformation, and I'll be talking about that a little later too. And then, of course, they make political contributions and they lobby their heads off. So it becomes very difficult to pass the kinds of policies that would favor the spread of clean energy. There are a lot of unfavorable regulations. And of course, there's political polarization, which seems to have reached a fever pitch right now. And that is muting public support. So despite the bumps, there is a lot of good news. And I want to share some of that with you today. All right. Despite a predicted 50% increase in demand, this is for the US, a 50% increase in demand for 2024 relative to 2023. Renewables are on track to reduce fossil fuel use this year. So here's a graph from a report by the nonprofit outfit Ember. And here are various types of energy sources, solar, wind, hydro, et cetera. And here's how much each one contributed in 2023. So here's solar. So the height of the bar is the number of terawatts of power that this form of energy contributed. So here's solar, here's wind, here's hydro. Bad year for hydro last year because it was so dry. Nuclear, other, which I'm not exactly sure what that is. I wasn't able to find it in the report, but whatever it is, there's not very much of it. And here's fossil fuel use. Okay, so this is how we got our power and satisfied this amount of demand in 2023. In 2024, a lot more solar, almost twice. Okay, more wind. Hydro is back in action, I guess, because there's been better rain. Nuclear, other. And then here's the amount contributed by fossil fuels. Whoa, minus 330. So this is a decrease in the use of fossil fuels, again, projected for 2024, even though demand is a lot bigger than it was last year. So I think that's pretty good news. Let's talk a little bit about progress in the particular arenas of wind and solar. And again, you can see that here's 2000 where nothing's happening, right? Except in Spain. Spain's been just really cooking ever since 2000. But the rest of the world, you can see, is on that sort of S-curve trajectory, which will come up and then sort of peak out at 100%. Spain is the big winner here, Australia and Chile. Next up, United States, China. Here's all of North America. And then there's the world. So wind power is increasing. Solar power is really increasing, okay? Well, it's on a slightly different scale, but it's increasing pretty steeply. Again, from Nowheresville in 2000, increasing up a sort of exponential looking type thing, which is going to be on the S-curve. And here, so Chile, Australia, and Spain, big on solar. China, US, the world, North America is down here. Okay, so, but still increasing. So things are looking good in terms of increasing use of wind and solar. More progress on solar. The prices have dropped pretty much exponentially. So here's residential solar. Here's from 2000 to 2023, small non-residential. So these are small utility arrays, utility scale arrays, large non-residential. And this is dollars per watt. Okay, so this is now, still pretty much half of this. So residential solar is the most expensive. The other thing that's happened that's really great is that the efficiency of the panels has increased. So these odd bars is percent of the sample from 0 to 100. Back in 2001, efficiency was less than 16%. And as time has gone on, you can see rise up a little bit in the turquoise, then the darker blue, 17 to 18%, the dark blue and the green, 18, 19, and 20, and then the yellow panels that are greater than 20% efficiency, which means 20% of the energy coming in from the sun is converted to electricity, which is really great. Because of the price drop and the greater efficiency, so a panel of a given size is now generating a lot more power than it used to back in 2000. The size of residential arrays on people's rooftops has increased at a pretty good clip. So that's great. I put solar panels on my roof in 2008, I think, and I have a 4.5 kilowatt system, okay? And now the average size of systems is 7.4. So when my solar panels get to be 25 years old, which is about the end of their useful life, I can take them off and replace them with much more efficient panels. And I'm not able to cover all my power use now, but I will be once I can have a set of more efficient panels. And we'll talk about recycling solar panels in a little bit. Okay, now geothermal heat and power. Geothermal is really cool. And there are two basic kinds of geothermal heat. This one I was familiar with before I started doing all this reading. And that is, so here's a neighborhood. This works for either one house or many, but there are pipes from the house that take water down into, I don't know, 100 feet or something. I think maybe even less than that, where the temperature is a constant 55 degrees, okay? So what happens is depending on whether it's winter or summer, the fluid coming from the house is either hotter or cooler, it doesn't matter. The point is, it's cooler underground in the summer and warmer in the winter than the ambient air. So if you remember how heat pumps work, they take the inside air, and let's say it's winter, and the inside air, you want to warm the inside air. So the inside air cools off, it goes outside, and it exchanges heat with the outside. Amazingly, it's able to do that even if the outside is cold. And then it comes back inside and warms up your house. So if the heat pump is trying to exchange with air outside that's like, I don't know, 20 degrees, it's going to have a lot harder time exchanging, gaining some heat from that than if it's 55 degrees, okay? Same thing in the summer. It has a harder time dropping off the excess heat if it's 90 degrees outside than it does if it can drop it off into 55-degree, fluid. So I hope that made some sense. But the bottom line is that when you can use this sort of constant 55-degree fluid to exchange heat in your heat pump, it's a lot more efficient, okay? And the pipes can be vertical like this, or they can be horizontal like this. It can curl around or not. They can even be in a pond, okay? So the idea is just to get this water from the house down to a place where the temperature is cooler in the summer and warmer in the winter than the air, okay? And this can be done for one home or many. This is very, very effective. Then there's enhanced geothermal. Enhanced geothermal is a kind of totally different, bigger scale thing. And in this sort of situation, the company drills down as deep as a couple of kilometers, okay? Drills down and then puts pressurized water through that pipe and creates a bunch of cracks in the rock. Now, the rocks down this deep can be as hot as 235 degrees centigrade, okay? In other words, really hot. Then these rocks get cracked and they drill a second well, okay? So when the thing is all, finished, they inject water down this first well and it goes into these cracks and these superheated rocks. And of course, that heats the water up. Then they bring the water back up to the surface and send it into a power plant where it's turned into steam, okay? Use the hot water for steam, and that spins turbines to make electricity, okay? So they use the naturally superheated rocks to heat water to make electricity. That sounds great. Now, this can have some of the same problems as fracking, like causing little earthquakes, okay? Now, unlike fracking, they don't inject a bunch of toxic fluids. So that's a bonus. They're just using water. But it can generate small earthquakes, not huge ones, but small ones. So it's not perfect, but once you've got the wells and you've got the pipes and whatnot, basically this is free. All you have to do is pump the water and then generate the electricity with the turbines. So here's some more. I will send out a slide handout, and you can get more information from some of these links if you're interested. I think this is really a great option. Okay, so we're at the stage now where renewables are starting to drive out fossil fuels for generating electricity and also for vehicles. The cost of wind and solar have dropped down pretty appreciably. There's been some supply chain issues since the pandemic has caused some problems, but the other sources of fuel, well, the fossil fuels and nuclear, much more expensive, okay? So now wind and solar are cheaper than these other things, and that's, follow the money, right? Here's a graph of annual electric generating capacity in the US from 2018 on. And you can see natural gas has increased a little bit, and I'll talk more about this in a minute, but renewables have increased a lot and are catching up with natural gas, especially solar and the gold here. Wind is sort of topping out for a few reasons I'll discuss a little bit later. But the great thing is that coal is declining, nuclear is sort of hanging in there. Geothermal is really not being used very much. Biomass is burning wood, like wood pellets, to generate electricity. That is not a clean energy solution. That it might be renewable, so-called renewable, because you can grow more trees, but it is not clean because when you burn wood, it puts a lot of particulates into the air. So I don't think biomass is a really great way to generate electricity. Okay. Now, the great news is, according to, again, this Ember report, these guys are reputable, so I think we can put our faith in this. Half the world has already passed peak fossil fuels. And so here's all of these different countries. This is one picture that I've broken into two. Starting with Slovakia, 22 years ago, they passed peak fossil fuels. And the second number is the change from this. So they're using 50% less than they were 22 years ago. Canada was the next one, 21 years ago. US, this is 15 years ago, we're only using 14% less. The UK, they're doing great. Australia sort of dropping down, etc. France, way down here, 5 years ago, they're using 12% less. So I think this is overall good news, right? None of these countries have completely ditched fossil fuels, but that's a good trajectory. Okay, now we all know that there are some barriers. One barrier, I'm happy to say, I think is a fake barrier, and that is how much land is required for solar panels. Now, I think, all of you have driven around and seen big solar arrays on farmland, maybe in forests like this. Some reports estimate that more than 10 million acres are needed for solar. And so people, understandably are a little freaked out about how much land that is. But I don't see why it's necessary to cut down forests like this or use farmland. Although I did see an article today of a survey saying 70% of farmers who were asked are willing to have solar arrays on their farmland if they can still grow crops, which is becoming more and more likely. Also, they're paid for this, so that's another source of income. But still, I think farmland is kind of a precious commodity, although there's another wrinkle on farmland, which is 70% of current farmland is used to grow crops to feed animals, beef and poultry. And, if we ate less beef, for example, we'd have a lot more farmland to spare. So nothing simple, right? Here's my point of view. Why can't we put solar arrays on industrial rooftops like this, these giant warehouses, which have, solar arrays on the roof? I did read an interesting comment about this, and that is that when you put the solar arrays on the roof of something like this that can't be seen from the parking lot or anywhere around, it completely quelches or squelches the complaining by people who don't want to look at the solar panels, or they say the reflection from the panel shines in my eyes or whatever. If they're up here, nobody sees them, and they're sort of out of sight, out of mind. But the point is, they're not on the farmland either. And so I think this is a great solution. And I have also read articles saying that there's more than enough territory on top of big box stores and warehouses to completely put all the solar panels we need. So there we are, industrial rooftops, or they can be put on what's called brownfields. That's like old sort of polluted sites where you don't want to build houses or anything. Last year, I talked about putting solar panels on top of irrigation canals, which shades them and is a good thing in general. Parking lots like this is where I want to park my car, right? I want to come out on a hot day, get in my car that's in the shade, right? This is going to be a big bonus while generating a lot of power. So I think that's good. The solar developers don't like to do this because they'd rather just plunk it down in the middle of farmland than have to, they have to build scaffolding for them anyway on the farmland, but they don't seem to like to do this. And the other cool place that solar panels can be put is on reservoirs. And this is called photovoltaics, right? Floating the panels on the reservoirs. And that causes some shading, et cetera. But if you're not covering the whole reservoir, that's not a problem too much. And the great thing is that the water keeps the panels cool, which keeps them running at a more efficient rate than if they're out there in the hot sun. My point, okay? Yeah, we'll need a lot of area to put the solar panels up, but there are a lot of options. Don't just grab that easiest solution, okay? I'm not a solar developer, so I don't have any way to basically make that happen, but that would be my vote. Okay, now, barriers to 100% clean energy, recycling and the supply chain. Right now, most solar panels and wind turbine blades, which do wear out, go to landfills. Here's a bunch of wind turbine blades cut up and put in a landfill. They're covering up with soil. This is not a great thing to do. So we need to have a better alternative to that. Recycling of solar panels and wind turbine blades is basically at the startup level. That is, there's these little companies who have methods to do the recycling, and some of them will, persist, and some of them will go out of business. So we're sort of at this very beginning of the process to recycle solar panels. So here's what a solar panel basically is made of. There's an aluminum frame, there's some glass, there's a polymer layer, there's the solar cells, there they are. Then there's 3 is more polymer and more glass, and then there's some junction box where all the electric stuff is. Solar panels can be recycled, okay? All this stuff, the frame, the glass, etc., that's easy. That's already just regular material and can be recycled easily. The panels have to be taken apart. The difficult part right now is the solar cells themselves. So here are a bunch of people who have taken apart a bunch of solar cells, and here's the business end of the solar panel, the layer with the solar cells themselves, and they've got them rolled up. Now, there are a few companies that are doing this, but it's not by any means a big solution right now. The other thing about solar panels, though, and I wasn't aware of this either, is that once the panels, they decline in efficiency over time. And, they'll be pretty good for maybe 20 or 25 years, but then they have really not enough efficiency that you want to keep them on your house. But they can be reused in other settings. For example, you could move these low efficiency solar panels and use them to charge up electric bikes, or you could use them to charge electric vehicle chargers, something like that, instead of generating electricity for your house, which is a more sort of demanding use. So you can reuse the panels. If you can't reuse them, then hopefully we will be developing recycling at a greater speed in the future. Wind turbine blades. Some startups recycle the old blades, and the development of fully recyclable blades using recyclable materials in the manufacture is underway. So here's an article in the New York Times last month about that. The recycling of old blades requires them to be sort of cut up or shredded, and then they get the carbon fibers out of them and use those to make new wind turbine blades. Okay, so that's recycling. I would say it's sort of at the basement level right now, but everyone knows we have to, speed this process up. This is part of the energy transition. With solar panels, we have some supply chain problems, and that they really hinge on this, that US made panels are more expensive than imports for a bunch of reasons. Chiefly because other countries use cheaper labor. Okay, it doesn't cost them as much to make the panels, but they're not paying their workers a very good wage, and they may be using unsustainable practices, which we really wouldn't support in the US. So, nothing's perfect. I think that's that should be our motto for pretty much everything. Nothing's perfect. All right. Barriers to clean, 100% clean energy. Transmission lines. I know some of you have probably read about that. There's not enough transmission lines to connect users who want to use the power and areas that have huge wind and solar potential. So here's a map, and here's a wind and solar installation, and they want to move the power over here, and that takes a new transmission line. The other thing, I'll just cut down to here. Thankfully, 4 new lines were approved in the past year, and those are shown on this graphic. And here's the link if you want to follow that. The other thing that happens, and I've read about this happening in Texas a lot, is that the transmission lines get so busy, that is, they sort of can't handle any more moving any more power, that the power basically just gets dumped. That is, it's not used, and usually this is wind or solar power. And that seems like a tragedy because, hey, the power was generated, but now it's not being used because we can't move it. The great thing is there are some really clever solutions to the transmission line problem. The first one is called reconductoring. Okay, and that means replace the current wires using the existing transmission towers. Okay, replace the current lines or the current wires with those that are more efficient. Okay, so here they are, the existing situation. Replace the existing wires with advanced conductors while reusing the towers. This is great because if you can reuse the towers, you don't have to get all the land to build a bunch of new towers, right? So this is really efficient. And then connect those new clean energy projects to now the expanded transmission lines. Okay, the second one is called clean repowering. And that involves building new wind and solar arrays near either an existing power plant that has, the surplus ability to transmit, right? So here's an existing power plant. You can add batteries or wind and solar and transmit the power down these lines because there's extra space. Or you could build your new renewable power array next to a retiring power plant. So here's a power plant. It has already dedicated transmission lines, but now it's not going to be generating any power. So you can just send this power down the lines instead. This is great, right? Because clean repowering doesn't just save time. Here's what the standard interconnection wait time is: 4 years. They think they're going to get it down to maybe a year, but here's the time if you do the hook it up to where a plant was retiring, maybe 11 months. And here's if you can just add on maybe 8 months. So it saves a lot of time to be able to do this. How smart is that? I really like that. The other thing is it saves a boatload of money, because instead of having to build a whole new, transmission line, get the permission, buy the land, pay for the land, build the towers, etc., just, put on the new wires. A lot cheaper. So I'm encouraged by this kind of smart and to me, clever. I mean, I'm sure all the people in the power industry have known about this forever, but this is a really great solution. Instead of just saying, oh, we don't have enough transmission lines, let's just guts it out and build a whole bunch more at huge expense and time. Let's do these things that take less time. Okay, and then there are a few more solutions which are really available now because we have enhanced computer abilities that can allow the grid operators to sort of move power around at will. So the first option here is what's called dynamic line ratings that adjust the carrying capacity of the transmission line based on real-time measurement of what is needed. So they give, for us regular people, right, they give a transit analogy using cars. So that would be as if the speed limit on the road drops down to 25 from 50 when the weather is bad, okay? That's smart, right? Because it's not safe to drive fast, so they drop the speed limit. That's dynamic line ratings. They adjust the ability to basically manage the demand. Advanced power flow controls, hardware solutions that push power away from lines with capacity constraints, and they pull power to lines with spare capacity. So that's like saying, you have a railroad switching station, so it switches the trains to the free tracks. That's smart, right? Of course, it requires enough computing power, and the grid operators have to be able to manage it. It's not just a simple option of, okay, go to work and make sure the wires don't fall off or something. You have to really pay attention here. Topology optimization. Topology is like shape. And these are software solutions that automatically route power flows around congested areas. That's like rerouting the drivers around traffic. Again, very smart. So there's more to managing the grid than just hooking up the power to the lines and letting it rip. Again, I think this is very smart. Now we're going to turn to building electrification. So the first question is, well, why electrify buildings at all? Why not just keep using, say, natural gas, which is very commonly used for cooking, for example? The problem is, not only does the use of natural gas cause emissions of methane, which are 20 times more potent than CO2 as a climate warming gas. Natural gas in your home is not all that safe. Some of this information came from a study that was run at Stanford, and here's a Stanford graduate student who was sent out to somebody's house with some implements to measure, leakage and what else is coming out of the stoves. When you use a gas stove, it emits nitrogen dioxide, not good to breathe. Benzene and formaldehyde, you probably already know these are terrible to breathe. And PM 2.5 particulate matter, smaller than 2.5 microns, really small, like little soot stuff. And this is what is so damaging in wildfires. Very, very bad to breathe. One of the worst things you can breathe in. It turns out that research has shown that almost 13% of childhood asthma cases are associated with using gas stoves. Okay, so homes that have gas stoves and use them are more likely, their kids who live there are more likely to have asthma and also other childhood respiratory diseases because they're breathing the, combustion products of natural gas. Having asthma then also increases the harm from this stuff. Other studies have shown that women who live in homes with gas stove have increased mortality compared to women who live in homes without gas stoves. And it's important to recognize that, even opening the window, but certainly regular home ventilation, even if you live in an old house that's kind of leaky, is not effective in, getting rid of these fumes in your home. And they can even, they're sort of distributed throughout your home, even up into your bedroom if you have a 2-floor house. So it's really not particularly safe to use a gas stove, especially if you've been conscientious and you've had energy efficiency improvements and sort of sealed the home up a little bit. So, well, what are you going to do if you have a gas stove? If you really want to keep your gas stove, you can install a vent to the outside and use it every single time. So a lot of stoves have, range hood fans, but you have to be careful that those actually vent to the outside because a lot of them just shoot the air back out into your kitchen. Of course, that's not going to do you any good. If you are interested in not using your stove as much, you can try heating up your water for tea or coffee in an electric kettle, and you can use an induction hot plate. So the most efficient kind of electric range is an induction range, and you can get a little hot plate, like this, for like less than $100. I bought one years ago when a genius friend of mine was teaching me about induction ranges. And I've had this thing for a long time. I've been using it a lot recently. It's great because it's much faster than my regular electric stove. And it is pretty much just as fast and just as nimble as a gas stove. So you can increase the heat or decrease the heat very rapidly. Or you could just go ahead and replace your gas stove with an electric. And if I were replacing mine now, I would get an induction stove with convection heating in the oven, a fan that blows the heat around in the oven, which makes it more efficient. Okay. Even though gas stoves are not very good for you, of course, the natural gas industry doesn't want you to either know that or care about it. And so when cities pass laws against using gas in new construction, as for example, Berkeley, California did, the gas industry fights back, takes them to court, and most of these have been overturned, which is kind of, well, depressing. Okay, building electrification. Let's carry on. Heat pumps. Heat pumps are more efficient than gas furnaces in all climates, okay? Even Maine, for example. So people think, well, heat pumps don't work if it gets very cold. Well, the new heat pumps are very efficient and they go down, to, easily below freezing. And so you can save a lot of money in all these states that get cold in the winter with a heat pump. Depending on your current heating equipment, natural gas furnace, electric furnace, propane furnace, average annual savings, a little bit over a natural gas furnace, electric furnace or propane furnace, you can save a boatload. If you are heating your house with baseboard heaters, you're really spending a lot of money, and you can save a lot if you change to a heat pump. Fuel oil, also, you can save a lot. Natural gas boiler, ditto, you can save a lot. So heat pump heating and air conditioning. Okay, heat pumps do both things, right? In the winter, they heat. In the summer, they air condition. So you don't have to have a separate air conditioner. And compared to oil furnace, baseboard, gas furnace, et cetera, the carbon emissions from heat pumps are lower, a lot lower than oil furnace, and they're cheaper, a lot cheaper than some of these things. Okay, I didn't calibrate these two things from different sources, but the point is, a heat pump will make your home comfortable. It will be very efficient. It will reduce carbon emissions from your home, and it will save you a lot of money, regardless of where you live in the US. Heat pump water heaters also available. Also, you can get rebates for those. And it's the same story, more efficient and lower emissions. Okay, now building codes. You might think building codes, it doesn't really have to do with me. These are for residential building codes. States with better residential building codes save money and reduce emissions because the code dictates what level of equipment you need to have, right? And how essentially how dirty it can be. The two laws I talked to you about before are providing a lot of money for updating the building codes and also for electrifying your home. So the interesting thing is, here's how much would be saved in your state if they updated the building codes. So the dark blue states already have really good building codes. People there would only save less than 5%. But Arkansas, people in Arkansas would save up to 35% on their energy costs every year if the building codes were more stringent. Now, of course, the building industry doesn't want the building codes to be more stringent. So that's how that works. Okay. How much can you save if you make your home more energy efficient? Okay. So incentives from the Inflation Reduction Act, the state you live in determines which of these you would be eligible for, but you can save up to $8,000 for an electric heat pump. The highest rebates are going to go to low and middle income households. You can save $4,000 upgrading your electrical panel so that you can run more electrical things, $2,500 for wiring, et cetera. So the rebates are pretty good. Here's a map of the US. The problem is, I think I alluded to earlier, that there's all kinds of delays in getting the money flowing from the Inflation Reduction Act. And states have, for the rebates, states have to actually apply for the ability to give out the rebates, and then they have to be approved, et cetera. So there's a whole process here. And so the turquoise states have submitted their application but not been approved. And the states in orange, they've been approved, but they haven't been able to get it together, get the rebates available. Only these 4 states actually have the rebates available. But this is, again, everything takes more time than you think. This is all coming down the pike. The IRA incentives are available till 2031. So that should work out okay. But even if your state, like Maryland, hasn't even prepared, or they're preparing their application, okay, so they're still at the beginning. Only South Dakota decided they didn't want to participate. Even if your state doesn't have the rebates yet, you can still claim tax credits on your income tax. And so I included these links where you can find out about that. If you want to know everything about how to get your rebates and tax credits, et cetera, you can go to the Rewiring America site, and here are some links for that. They even have your personal electrification planner to help you along with this process. Okay, electrification of transport, electric vehicles. This is in the US. Here's where we are now, pretty much nowhere. We're at 12% projected for this year. So we're at the beginning of the S curve here. But it's very likely that progress will be even faster than this. Okay, this is projected 89% by 2050, because pretty much every prediction made by the outfits that do these predictions have been revised upwards every year, sometimes substantially. So even though this projects, maybe 22% in 2026, by next year, they could be projecting 30% or 35%. So this could really occur a lot more steeply in reality. All right, so batteries for EVs. Batteries do introduce some problems, which I'll discuss in just a sec. The main type of batteries are lithium-ion batteries, and the prices for both stationary storage, like Tesla Powerwall, I guess, or something in your basement, and passenger EVs are declining a little bit. And more and more utilities are investing in battery backup. You can see nothing was happening, and just a few years ago it started to happen. Here's Here we are in July 2024. The batteries, lithium-ion batteries use 5 main minerals: lithium, nickel, cobalt, manganese, and graphite. These minerals are concentrated in just a few places, a few countries around the world, and the mining of these minerals is associated with a lot of human rights abuses and environmental degradation. This is like the big issue with batteries. The U.S. is working pretty hard to try to clean up and strengthen the supply chain, but the problem is a lot of the mining is done sort of by families. There's not much regulation, et cetera. Now, there are some other ways to get lithium. For example, I didn't include that on the slide. There's a small amount of lithium in seawater, and you can evaporate the seawater and get the lithium that works, but there are also some alternatives. Here's some information from, again, the Rocky Mountain Institute. They outlined 6 solutions for curbing the battery mineral demand: change the chemistries, recycle the batteries, more efficient vehicles so they don't need as large a battery, raise the energy density, that's how much energy you get out of the battery, reuse the batteries and extend the lives, and efficient mobility means basically use the train or the bus, okay? Sort of get out of your car. If we use all these things, they predict that we'll have peak battery mineral demand in just a few years, basically. And once you're recycling, once you've got the minerals, then you don't have to go back and get more. 3 out of these 6 solutions are already helping, okay? Here's 3 of the minerals: lithium, nickel, and cobalt. Here's the actual demand in the dark blue. And here are the avoided demand due to chemistry changes, that's in the gray, density improvement, that's in the turquoise, recycling is in the blue, okay? So they're recycling more cobalt than lithium. And second life use, that's basically like taking your old EV battery and putting it in your basement to sort of use as power storage. That's second life use. So this is helping a lot, and these things will continue to help. So I think that the issue with the minerals for the batteries, even if we stick with lithium ion, is going to sort of even out in a few years. So again, I mentioned that we could reuse the batteries that are no longer useful for EVs. You need to have a pretty good battery to run a car. The battery can be not charging up to full capacity and still be used for energy storage. So that's good. After reuse, the batteries can be recycled. So, you can really wring everything out of these batteries. Here's recycling capacity up to 2030. And again, according to RMI, announced recycling capacity is already enough to handle all the batteries we're going to have through 2030, but they need to ramp it up to be prepared for after that. Most of the battery recycling right now is occurring in China or in Europe, a little bit in the United States, and then the rest of the world. But China is really leading the way here. Now, the other cool thing is that there are new battery chemistries. For example, you can make batteries that don't even use lithium or cobalt, manganese, et cetera. And these are sodium-ion batteries. So they use sodium. Well, sodium is super, right? Sodium's what's in salt. Sodium's super common. You don't have to go to the Congo to get sodium. Here's one company, Natron Energy, and they advertise the properties of these sodium-ion batteries, and their characteristics are very favorable compared to lithium-ion. They take less time to charge. They're not flammable. Lithium-ion batteries are very flammable, which is like a problem. You can charge them many more times. That's deep charge cycles. You can charge them 50,000 times, which is a lot. They have better operating temperature, et cetera. So there's a lot of advantages to this, and they love the way this looks. Their blue pack. This is one of those batteries. So again, there's more information. Here's an article from the BBC, which gives you a lot more information on battery reuse and different chemistries. Here's a really good idea that doesn't require you to have a battery. I'm closing in on the end here. I realize that we're getting a little bit late, so I appreciate your indulgence. You can focus the sun's energy directly onto bricks. This article just came out like 2 days ago. I thought it was so fascinating. These are not solar panels. These are like lenses that focus the sun's energy down onto this big container of bricks, essentially. and these get super hot. Then the people in charge can take the heat and from the bricks and focus it onto thermovoltaic panels that turn heat into electricity. So photovoltaic turns light into electricity, right? So they can then generate electricity, or they can just use the heat directly in industrial processes, which take a lot of heat. Making food takes actually a lot of heat: steel, cement, glass. And in some cases, this is one of the the big containers of bricks. They just use renewable energy to heat the bricks up directly, and then they use them in these industrial uses. The great thing is it costs less than 15% of what it costs to store energy in batteries to store energy this way. So again, smart idea. I like that. This is the last main topic. Virtual power plants use what they call distributed power to help the grid. So distributed power is like a rooftop solar, photovoltaic panels, distributed batteries, and electric vehicles. So these are sources of power. They have batteries, or they're generating electricity. And then demand or load is managed by your thermostat. That's for your furnace, smart water heater, and commercial automation system. So these are the devices that customers have. They have sources of power and they have demand. Customer devices are managed by an aggregator when power is needed. The aggregator reduces demand, basically sends a signal to your thermostat saying, well, you're not going to be able to run your air conditioner for a few minutes here, maybe half an hour or an hour. BGE already does that. They pay you to allow them to, cycle your air conditioner. They're not making you give them this ability for free. They're paying you, and that's what happens in these virtual power plants too. So they reduce demand, or they grab some of the supply from your EV or batteries or solar PV as needed. So this requires something that has not been present in power systems up to recently: bidirectional power. So in the past, we get power from the utilities, we get it out of our plug, but we can't send power back to the utilities. Now, many of the EVs and other sources of power allow you to have sort of connections that allow you to send the power back to the utility. So here's the power system. The power system operates at lower cost, and it's more reliable, also less emissions. And you don't have to build a bunch of new power plants because the power is basically being taken from the consumers. They're being paid for this, okay? It's not, if you're in one of these places where they offer you a virtual to participate in a virtual power plant, you don't have to say yes, you can say no, but they're going to pay you to do it. And then basically the benefits are shared by the customers and pretty much everybody. Having a VPP, a virtual power plant, improves the grid reliability because there's power available, and the grid operator can sort of turn down the demand by requesting that consumers use less power at certain points. Virtual power plants will have many more assets to recruit as more demand is internet connected, as more people have smart water heaters or internet connected furnaces or whatever. And that allows demand flexibility, okay? And also commercial flexibility. So this reduces the need for power. On the other hand, there's a lot of small scale battery storage, electric vehicles, solar panels, et cetera, and these things can send power to the grid. So this all helps in a big way and allows utilities not to build a bunch more power plants. That's good news. So virtual power plants can save billions of dollars. With a virtual power plant, you don't need to build a new power plant or transmission lines to manage an increase in demand. I've been reading recently how Duke Power and Georgia Power are both planning to build a lot of new gas-fired power plants because of the increase in demand given electrification and EVs. So they're just building these new gas-fired power plants, which are going to be obsolete way before they actually wear out. So this is, of course, all going to be charged to the ratepayers in these areas. And they should just be, coming up with a plan for a virtual power plant. Instead, they could do that. If you have a virtual power plant, you don't have to build a lot of utility scale battery storage. EV batteries in virtual power plants could provide the same power as fixed batteries worth up to $15 billion. That seems like a huge bonus. And you get paid to allow the utility to take some of the power out of your EV battery when you're not using it. I mean, you're going to be paid more than it will cost you to charge it back up too. So that's important. And the utilities don't need to use peaker plants, which are generally very dirty, to cover peak load, like big air conditioning moments. Using VPPs instead of more power plants also reduces emission, improves health by reducing air pollution from generating the power. And this is key. It involves people in their own power use. Once you realize, well, I could let them do this and they're going to pay me X amount of money. That seems like a pretty good deal. That's going to cut my utility bill in half. And it really doesn't cause me a lot of inconvenience. So why not? I've sort of experienced this for myself when I got solar panels and I realized, I could go out and watch my electric meter spin backwards, which, that gave me a real kick. Call me strange, but I thought that was really great. But I started to be really aware of how much power I was using after that. Here's some actual modeling done by the Brattle group. Here's the cost of providing 400 milliwatts of essentially power. If you get it from a gas power plant, it's going to cost this much, 40 some million dollars a year. Battery, maybe $30 million a year. Virtual power plant, whoa, a couple $1 billion a year. So this can save a lot of money. Instead of asking ratepayers to pay for new power plants, the utilities can give the ratepayers the money back. Okay, with current technology, we can replace 70% of fossil fuel use essentially already. Okay, so here's the fossil fuel system. Here's wind and solar. Here's electric vehicles cutting into this fossil fuel use. Here's heat pumps. So this is pretty much 70%. Then there's hydrogen. These are things that still need to be done. Hydrogen and the so-called harder to solve sectors, which are things like cement, steel, aluminum, aviation. But there's actually a lot of cool things going on here. So they're really not going to, this is not going to be a problem for too long. Again, according to RMI and some other people, we are very likely to have solutions for the rest of this stuff by 2030. So probably fossil fuels are going to be on a steep slope out of here by 2030, which would be a really great thing for the planet. Barriers to the energy transition. There's a lot of disinformation out there. Disinformation has really gone wild. This is disinformation in the media, which is being planted by fossil fuel interests. And here's a nice report from the Energy and Policy Institute. Here's the link that documents that. It's really annoying, well, aggravating. It misinforms the public. It reduces the support for clean energy because people think, oh, we don't need to change. But it's all being paid for by fossil fuel companies. And of course, then they lobby the politicians to block all the policy we need. The culture war, so-called culture wars, and all this political polarization we have of lawmakers and the public is really blocking or limiting the policy we need, and it's eroding public support for the transition. By spreading information that's wrong, intentionally wrong, that's disinformation. Misinformation is when you don't know you're saying something wrong. Disinformation is, I know I'm lying, but I'm going to do it anyway. People are probably the biggest barrier to the energy transition. Although 70% of Americans, according to the Pew Research Foundation, want more renewable energy, here they are. They want to prioritize developing alternative energy, and they want the U.S. to take steps to be carbon neutral by 2050, 70%. They don't want to end fossil fuel use. Okay, it doesn't really make sense, but there it is. People often hold contrary ideas in their mind. All of U.S. adults favor, this is 67%, favor a mix of energy sources, including coal, oil, and natural gas, along with renewables. And this varies by age. Thank goodness the young people are going to help us out here. Old people in my age group, not so helpful. But we've seen this over and over. Americans don't want to be told they need to do something. Don't make me wear a mask. Don't make me buy an EV by 2030. Don't make me do anything, even though it's for the social good. Okay, I don't want you to make me do it. I don't agree with that, but there it is. Okay, And then there's disinformation that's spread by people on social media. I'm not on social media because I don't have any patience for that, but there's a lot of disinformation on social media. Here's a few posts that this guy who writes this distilled blog, he's a reputable guy, has provided. Here's a post talking about so-called wind turbine system, which is supposed to be some medical problem caused by wind turbines. No evidence for this, okay? Here's one. Does anyone ever wonder how our volunteer fire department would fight a turbine fire like this? Well, there are no documented turbine fires. I don't know where they got this picture, but there's no evidence for this. This is disinformation because it's willfully wrong. I mean, maybe people think they're right, but I doubt it. Then there's the sort of NIMBYs, not in my backyard thing. People don't like the noise or the flicker of the sunlight from wind turbines, or they don't like what solar panels look like. And then you've probably also read that there was some information that offshore wind was affecting whales. Well, that's been totally debunked. It turns out all the damage that was documented to the whales was caused by ship strikes on the whales, not by offshore wind. But as a result of all this, people go to their county council meetings or their county meetings and they say, I don't want this project here. And so wind and solar projects are now delayed or halted by local opposition in more than 30 states. This is setting us back, people. And so again, try to be aware of this. Last slide. What can you do to help? I know everybody on this webinar wants to help, okay? And that's one reason I love giving these webinars so much. So here's what you can do. You can keep learning like you're doing now by coming to this webinar, reading a paper or other things. Keep learning and show up to stuff, write letters, talk to people in your network, at church, at your work, etc. So here you are. Let's talk about how we can stop climate change. Then your two friends who you tell, each tell two more friends. And before you know it, a lot of people are, talking about this. Encourage your federal, state, and local representatives to vote for needed policies or call them out on that. Then vote them out if they're obstructing needed policies and wasting their time on culture war stuff, which is getting no one anywhere. Learn how to recognize disinformation and teach others to recognize it. I think students in every high school should be taught to recognize disinformation. Stick with reliable, verifiable sources for information. If someone says, I saw this on TV, nah, that's not a reliable source. If you read something, but there's no link to an actual, scientific paper or some reputable source, don't believe it, right? Stick with reliable, verifiable sources. Electrify your own home and talk it up to your friends. I got a new heat pump. It's really great. My home is more comfortable. It's saving me a lot of money. If you rent, encourage your landlord to electrify. And the last ditch, make your voice heard and march if you have to. Trust scientific facts, not alternative facts.